Hello, this is video number 19 on my single variable calculus 2. In this video, we're going to go over sequences. A sequence is a list of numbers. The nth term of a sequence is generally denoted by an, bn, cn, or etc. The sequence an is denoted by an with curly bracket on the two sides, and then we put the limits of the index to the right of it. So n equals m to infinity. It means the first term of the sequence is am, the next term is a sub m plus 1, etc. So for example, for the sequence that starts with a3, we have an, n starts from 3 to infinity. We say a sequence converges if the limit of an as n goes to infinity is L, and that value is a real number. And this is sometimes written as an, and then we have an arrow L. So that means an approaches L. Otherwise, if the limit either does not exist or the limit is infinity or negative infinity, we say the sequence diverges. So we're going to go over a few examples of evaluating the limits of sequences. So this is really nothing new. This is basically the same stuff that we have learned before, except that keep in mind that n is a positive integer. So we want to figure out if the sequence -1 to the power of n converges. In other words, when n goes to infinity, does this approach a specific number? Well, for n equals 1, we have 1, -1. For n equals 2, we have -1 squared, which is 1. The next one is -1 cubed, which is -1, -1 to the fourth, which is 1, -1, 1, etc. So these values do not converge to any specific value. They alternate between 1 and -1. So that tells us that the limit does not exist. Okay, let's look at the next example. The next one is 1 minus 2 over n to the power of 2n. Well, let's see what happens if we plug in infinity for n. If we plug in infinity for n, we get 1 minus 2 to the infinity, which is 0, to the power of infinity. So this is 1 to the infinity, which is an indeterminate form. So we'll have to use the L'Hopital's rule after taking the natural log. So we take the natural log of 1 minus 2 over n to the power of 2n. We put the 2n up front. We get natural log of 1 minus 2 over n. Now, what is the form of this indeterminate form? So the form is, well, 2 times infinity is infinity, and then natural log of 1 is 0. So this is infinity times 0. In order to evaluate the limits of infinity times 0, we have to put one of them at the bottom. So we will take natural log of 1 minus 2 over n, and we put 1 over 2n at the bottom. And we're taking this limit as n approaches infinity. When we look at the numerator is natural log of 1, which is 0, and the denominator is 0. So we can use L'Hopital's rule for this one. If we apply L'Hopital's rule, we are going to get the limit as n approaches infinity. The bottom is 1/2 and then minus n to the power of -2. So that's the bottom. The numerator is 1 over 1 minus 2 over n times the derivative of denominator, which is 0 minus -2 n to the power of -2. So let's simplify and then take the limit. So this is the limit as n approaches infinity. Well, 2 at the bottom comes to the top. We have a positive sign on top. We have a negative sign at the bottom. So we get -4. We also have n to the power of -2 that we can cancel. And at the bottom, we get 1 minus 2 over n. Now, when n goes to infinity, this becomes -4 over 1. So now what is the limit of the function, the sequence that they gave us at the very beginning? Well, we can write this down as e to the power of the answer that we got from here, which is -4. So the limit for this one is e to the power of -4. Let's look at the next one. So the next one is sine of n over n. We want to find the limit of that. Well, if you look at sine of n oscillates between 1 and negative 1, but at the bottom we have n that goes to infinity. So it looks like you have a small number divided by a very large number, so it looks like the limit is in fact 0. But how do we justify that? Well, we can squeeze this function between two functions, between negative 1 and 1 over n. So both of those are over n. So now we know that the limit of negative 1 over n and the limit of 1 over n, they are both 0. So then we can apply the squeeze theorem and then that the middle and then say that the middle one would have to be 0 as well. So by the squeeze theorem, the middle limit would also be 0. So limit of sine of n over n is 0 as n approaches infinity. So that's the answer to this part of the problem. Let's look at the last question that we have here. So this is nth root of n. So if you look at nth root of n, every root can be written as an exponential. So we get n to the power of 1 over n. So what is the form of this limit? Well, the base is infinity, and then the numerator is the exponent is 0. So this is the form. So we'll have to take the natural log. So natural log of n to the power of 1 over n. This is natural log of n over n. So when we take the limit as n approaches infinity of natural log of n over n, this is again an indeterminate form, natural log of infinity, which is infinity over infinity. So we can use L'Hopital's rule again. So we get limit as n approaches infinity, 1 over n divided by 1. And of course, that is 1 over infinity, which is 0. So that tells us the limit of nth root of n as n approaches infinity is e to the power of 0, which is 1. Okay, so this is one of the techniques that we use in this example. It's called the squeeze theorem. So let's assume that we have three sequences, an, bn, and cn. An is between two sequences, bn and cn. Let's assume that bn and cn approach the same number l. Then the middle one, which is an, also approaches l. Let's do a couple of examples and then we will summarize at the end. Determine if each sequence converges. If it does, find its limit. Well, if you look at the first one, negative 0.9 is going to be between negative 1 and 1. So that tells us that if I take this negative 0.9 raised to the power of n, I would eventually approach 0 because it's a number between 0 and 1, between negative 1 and negative 1 and 1, which means when you raise it to large powers, it becomes smaller and smaller, and the limit is in fact 0. Now, for the second one, if you look at the limit of 1.01 to the power of n, as you increase this exponent n, the 1.01 approaches infinity. So this diverges. So the answer to this one is divergent. The answer to that one is converges to 0. So in general, if I look at powers of R, these are called geometric sequences. If I look at powers of a constant R, if that constant is between negative 1 and 1, this is the same thing as saying R is between negative 1 and 1, then r to the power of n approaches 0. If r is 1, well, then 1 to the power of n is always exactly 1. So it does approach 1. Otherwise, it does not converge. Okay, so here is what we did in this video. An converges whenever the limit of an exists and is a real number. To find the limit of a sequence, you would use typically the same strategies. You could use L'Hopital's rule, or you could use other techniques of finding limits. To find the limit of a sequence an using the squeeze theorem, find two simpler sequences bn and cn that squeeze an. In other words, bn and cn are on the two sides of an. Now show that bn and cn have the same limit, and then conclude that the middle one an must also approach l. And the last thing that we did was that for every constant r to the power of n approaches 0 if r is between -1 and 1, and it is exactly 1 if r is 1, and the limit does not exist otherwise. And that brings me to the end of this video. I will see you in the next video.